This is one of the major simulation engines that were used for biomolecular simulations, for protein and nucleic acid simulations, membranes, water, ions, etc. I think the major advantage of this program over other programs is that it's highly scalable. This has been actually developed, apart from the fact that it's been developed here on this campus, and that's also a major advantage. This has been actually highly scalable. You can look at the performance of the program, and if you compare it to competing programs, you can see that actually really nothing beats this. It has been developed here in the Langevin Institute, and over the last 15 years or so, we have always had quite a few computer science students working on the program, optimizing the code for parallel performance. And this has been achieved actually on any new platform that came online at different supercomputing centers. So it's really, I think it's fair to say it's a standard ND code for biomolecular simulations at our centers. We have the program also installed on NCSA machines, including the Forge machine that you can access to and run your simulations. The scalability is pretty good. It is available actually on all platforms, pre-compiled for Windows, Mac. I sent you the link. And so on Linux, Mac is no problem. On Windows, it could be a bit tricky. We can help you to get the program installed and running on your laptops this afternoon. So again, I mean, the theory and the idea and the algorithm we discussed to some degree, you know a little bit about it. Now there are specifics about how to run a NAMD simulation that I will cover to some degree, and then later this afternoon we set up the simulation and run it. So the example that you will use is ubiquitin. It's a protein that does some interesting biological stuff. We don't want to know about that. Let's not worry about that. So this is the potential energy function that we talked about. I have bonded terms and non-bonded terms. And now I need, before I can start propagating the before the program starts propagating the equations, calculating forces, we need to give the program all this information. We need to give the program the topology of the system, how many bonds for each bond, the force constant, equilibrium values, and all these parameters, as well as the coordinate of the system, should be introduced to the program. There are different ways of doing that, but in NAMD, sort of language, these are coming from the geometry. These are the geometrical relationship of the coordinates, distances, bonds, and angles. Then we have a set of parameters that need to be introduced, as well as partial charges. And now in NAMD language, we are going to deal with quite a few files. I think 4 different files you need to prepare. You need to have them before you can start a NAMD run. One is the PDB file. That's the coordinates of the molecular system. Then we have the protein structure file, or PSF file. It doesn't have to be a protein, but that's the traditional name for that, which includes the topology of the system, how many bonds you have, what is connected to what, as well as the charges, atomic charges. And then all the other parameters are stored in a parameter file. So if you have these 3 files, plus a configuration file, which is your control panel controlling the conditions, specifying the temperature, how long, what time step, what cutoff, etc., etc., then you have all the files that you need to run your NAMD simulation. So what you're going to do under ideal conditions, so today you're going to have all these 4 files on your laptop, set up a very short simulation, maybe 2, 3, 4, 5 picosecond of simulation on your laptop. Make sure that the simulation runs, everything is fine. And if that's the case, then you can copy all these files into Forge, your training cluster, how should we do this best? Should they submit like half-hour jobs, or
yes,
should?
Yeah. So we have about 8 nodes reserved for this class.
8 nodes.
Yeah, that's about 128 cores.
Mm-hmm.
So, yeah, they can,
Okay.
and then there's a reservation. So that means that all these jobs will be submitted in the reservation. So if they are running in short periods, then they should be able to get results.
Okay. So I don't think actually that everybody will have a large molecular system that really requires that supercomputing facility. But I mean, I highly encourage, especially those of you who are here, to learn about protein simulation because you have a particular protein or any other molecular system that you want to run. Start working on those systems here to learn how to run them and to run into trouble so we can help you. 3 of my group members are here that can help us with the lab sessions today and tomorrow. So this is a great opportunity to get things going and to learn the program. So if you, for most cases, you will be fine with your laptops. I don't think we need to have the Forge system. But if you have a fairly large system, you want to run it longer, then we should copy the files over to Forge, run the simulations there, and then we get the trajectory and output file back on your machines, and then we visualize the results locally.
Yeah, in a few minutes I'll write the path for the NAMD binaries.
Oh, excellent, excellent. I also asked actually my group members to have a sort of run batch type of script, so you can use as an example to submit jobs. But
there is also a run batch.
Oh, perfect. Okay, excellent. Then we are all set. Okay, but again, you will see that we need to provide these files. And now let's look at, actually, we will look at these files tomorrow a little bit so you know what information is there, how to change them. And that actually also is a good transition into coarse graining, because coarse graining is, I mean, you are essentially using essentially the same terms, but the definition of atoms and bonds and things of that sort are different. So everything is essentially done at the level of the topology and parameters. Coarse grain, protein, atomistic protein, everything is the same. You just change the topology and parameter file. Instead of having a methyl group described with 4 atoms interacting with another methyl group with 4 atoms, you have 2 beads that interact with each other, like 2 particles. They are bonded to each other. You will have a bond there, but the force constant is going to be different. The parameters that we will use for coarse graining is going to be different. So let's look at the configuration file. That's, by the way, I sent you an email about this tutorial. This is a PDF file that you can open on your laptop and then go through it. We don't want to do the whole thing. We will not. This is usually for 2 or 3 days of exercise, but we want to just cover the basics of NAMD in this tutorial, as well as basic type of analysis. So you learn how to run the program, how to get the simulation, and how to do basic analysis. There are advanced kind of examples in that tutorial, and you're more than welcome. If you feel comfortable already with NAMD, you can use those advanced examples and run those simulations. So, okay, so let's look at the configuration file. Again, the files that you need, the structure file is specified. Here you can actually use both TCL commands like sets, loops, and things of that sort, as well as NAMD-specific commands. You specify the structure, the coordinates are in this file. You set the temperature, that's your target temperature in Kelvin. And this is used to randomly assign the temperature. Anything that is set using the command set can be used later as a variable using the $sign. So you set this variable to 310 and then use that to specify the temperature of the system. You can have other variables. For example, the file name is just input files, all the input files. If they have the same kind of file name, you can specify that as a common variable here using the command set, and then use it in other commands That's a sort of TCL kind of scripting language. If you are starting a brand new simulation, of course, you have to specify the temperature, and that temperature will be used to assign velocities. If you are continuing a previously run simulations, you already have some velocities from the previous step, right? Always calculate the new velocities, new coordinates, forces, new velocities, new coordinates. So you already have a set of velocities and set of coordinates, so you can use those restart files to continue a simulation. You want to run a microsecond, half hour on Forge, you can only run 5 nanoseconds. You want to be able to restart the simulation exactly from the point that you ended. So there is a way of continuing the simulations that is specified in this block. Again, don't worry about the syntax and the details. Just know that there are these capabilities exist. So that's the main idea of showing you a little bit pieces of this configuration file. You can also specify the output file name, how frequently you want to save the restart files that you want to use to restart your job later, how frequently you want to save the coordinates. You are running every femtosecond, you are calculating the coordinates, forces, velocities, positions. So do you want to save the trajectory of this huge protein every femtosecond? Probably it gives you a very large file that you don't want. So you can specify how frequently you want to save the coordinate. And actually related to that, this is also specifying the size of the system because it fluctuates. You want to save the size, the extensions of the system at the same frequency as the DCD. But the DCD file, that's the file extension for trajectory showing the position or monitoring the position of the atoms in your simulation system. That is something that you will use later for your analysis. We usually don't save the velocities unless you really need them for example, velocity autocorrelation or other kinds of analysis. So usually we just monitor the position of atoms and to see how the protein or how the molecule is fluctuating and moving. The same applies. You can output the energies. For all the terms that we described in the potential energy function, you can have the energy at each time step or a certain frequency, as well as you can see how fast the simulation is running. You don't want to monitor this too frequently because that slows down the program. So, but every 1,000 step or so, you can specify that. It tells you how fast and how efficiently it is running. So you can monitor that. So as far as the simulation conditions, excuse me, is concerned, this is the name of the parameter file. So I told you need to have a parameter file. Excuse me. This is the so-called all-atom charm 27 parameter file for protein and lipids that we are using. If you have different molecular systems, you can use different parameter files. Okay, so that's something I forgot to mention. So when you are doing a molecular simulation, I told you all non-bonded interactions. Non-bonded interactions are calculated between every pairs of atoms. But if these atoms are bonded to each other, of course you don't want to recalculate non-bonded interactions because the interaction between two bonded atoms is described by a different set of rules. So bonded interactions are excluded essentially from non-bonded calculations. So now you do this for, of course, atoms that are immediately bound to each other. You do it for atoms that are connected through two bonds because they are connected through the bond angle. But when it comes to the atoms that are connected through three bonds, forming a dihedral angle, now the question is whether these two atoms in space should interact through non-bonded interactions or not. And the way the force field is set up is based on certain type of inclusion or exclusion of this 1,4 kind of interaction. So that's what you specify here, whether you want to have any scaling involved and any switching, any scaling or exclusion and inclusion. You specify this based on the force width. So cutoff, what is the cutoff distance that you use for calculating non-bonded interactions? Mostly for van der Waals, but also for some part of your electrostatic calculation. Switching distance, you start switching your function, going towards 0 at 10 angstrom distance. So by the time you reach the cutoff, your interaction is completely gone, so you don't have discontinuity in your energy and forces. So you usually, when you specify a cutoff, you usually also need to have a switching distance. Otherwise, if an atom appears and disappears from your cutoff distance, you will have discontinuity of your energy and forces. Exists, doesn't exist completely. So you want to have a smooth function connecting these two regions. That's specified here. Pairless distance. So again, you want to only calculate the interaction between every atom and atoms within 10 angstrom distance, but just calculating what atoms are within 10 angstrom distance is costly. You don't want to repeat this kind of calculation every time step, because you have to evaluate all the distances. So in order to avoid that, you would define a region that is larger than your cutoff, 14 angstrom. You find all the neighbors within 14 angstrom for each atom. And then this is not going to change in the next 10 or 20. So if you just evaluate atoms that are within 14 angstrom distance of your central atom, there is a very small chance that you miss any of the atoms for which you want to actually calculate the interaction energies. So by doing this trick, you will limit the evaluation of 12 angstrom distance atoms to a smaller region, and the likelihood that an atom moves 3 or 4 angstrom coming from the outside region all the way into the interacting region would be very small. So by this trick, you can evaluate the neighbor list. Instead of every time step, you can do this every 20 or 30 or 40, depending on your molecular system. So these are some conditions. Time step is specified here. For example, I told you 1 femtosecond is usually the regular time step. But if you rigidify some of the bonds, including the hydrogens, then you can take longer time steps. So that's what is specified here. Then you can have multiple time stepping. For example, non-bonded frequency. Every time step, you are going to calculate non-bonded forces. The non-PME part of non-bonded forces has full electrostatic energies, which are calculated using PME, will be done only every other time step. So this is the multiple time stepping, allowing you to make your simulation even faster. So this is about the Langevin dynamics. So we want to have, we turn on Langevin dynamics. That allows us to control the temperature. So we want to, the target temperature is the same temperature that we initially specified, remember, using the set command. We use that one also for our Langevin dynamics algorithm. This feature doesn't affect hydrogens. Hydrogens are too light usually. So you usually don't want to mess with hydrogens too much. If you are doing bias simulation, if you are subjecting atoms to some sort of random noise or other external type of forces, you usually don't want to include hydrogens. They have a very small mass, and their velocity can be affected significantly if you add forces to them. So we usually leave them alone and work with heavy atoms of the system. The Langevin dynamic damping coefficient, that's gamma that we talked. This should be actually 0.5. Please actually, even if you have 0.5, even if you have 5 in your example, please change it to 0.5. This is historically, I don't know if that's been corrected, but we don't want to damp the system too much. 5 is way too much. You see, I mean, we have a problem with time scale. The system doesn't move enough for us to see anything significant. Now you go in and damp it significantly, you're not going to see anything. So we usually try to minimize this just to have it enough to be able to control to some degree the temperature of the system. So please correct this to 0.5 in case it's still in the configuration file. So I'm going very quickly over this just for you to have an idea. If you have more sort of specific questions and you want to change this, we can discuss it more in the afternoon. So we usually use different kinds of periodic boundary conditions. And I think for that, let me show the next slide first. So this is our simulation. This is, let's say, this is your unit cell. This is what you want to simulate. But of course, if you don't have anything around it, all these atoms or molecules are going to evaporate into the vacuum, right? So you want to have something that helps you maintain the correct density of the system. And then at the boundary, these molecules don't want to interact with vacuum. So you should have something real here. So in order to avoid this problem, this boundary problem, we, instead of just simulating a simple system like this, we are going to copy the unit cell. The actual atoms only exist in the unit cell. But then we have images of the unit cell to the left, to the right, up, down, front of us, in the back, in all 3 dimensions. And these images, all these atoms follow the position of the atoms in the central unit cell. So by doing that, you will have actually, it looks like you have another box sitting to the right, to the left, to the up and down. So all the boundaries of the system will be occupied. For example, for a solvent, you will have solvent all around the unit cell. So here at the boundary, you will be interacting with other solvent molecules. So it's much more natural especially for a bulk system, to be treated in this, using this boundary condition. We call this periodic boundary condition. This is also required for PME, particle mesh evolved, calculating electrostatic without truncation. So you can see actually there is a lot of advantage without really increasing the size of the system significantly. We have taken care of having real boundaries for the system. This is the size of the boundary system is specified here using 3 vectors, x, y, z dimensions, and that's the origin of the cell. So there is this block is interesting because, so what happens in periodic boundary condition is that, so these atoms, let's say you start with a box of argon atoms, and they start diffusing around. After a while, the initial box that looked like a very nice rectangular box will look like a cloud in space. So if you want to monitor that, visualize that, things become a little bit messy. So in order to avoid that, what we do, we say with this wrapping command, what we do, we say, okay, if an atom leaves this box, that means its image from the neighboring cell would be coming in. So we stop monitoring the copy that left the box, and we start monitoring the position of the image. So that way, the focus will be always on the unit cell in the middle, and the shape of the molecular system stays sort of rectangular. It's nicer to visualize it, and certain type of analysis might be easier, et cetera, et cetera. The only problem is that if you want to really monitor the actual diffusion of these particles, then this wrapping becomes a problem because you artificially are reducing the total displacement of this particle from its original position. You're just bringing it back always. So in that case, you have to unwrap your trajectory or you turn off this feature. So this is what is specified here. So these are really just the most basic features that are specified in the configuration file. You can change them. You can, of course, use the default values, except for that gamma. Please check that. Otherwise, you can use the example that is provided in the tutorial files. So now, in addition to periodic boundary condition, this is I think the best way of doing things. It allows you to control the pressure as well, because you have a well-defined volume. You can actually change the volume to reach a target pressure. But it can be expensive because you have to include a lot of, for example, if you have a protein, you place your protein in the middle and you have to fill the box with solvent or other things. So that increases the number of atoms in the system. So for some cases, people have been using a different kind of boundary conditions. For example, you can have a spherical boundary condition in which you will have solvent around your protein, but then you're essentially cutting the corners from a rectangular cubic kind of cell. So this way you reduce the number of atoms. Of course, things are more difficult. It's a little bit difficult to control the pressure here, and you don't know if you have the right density of water within this sphere or not. But that can actually significantly reduce the number of atoms, especially if you have a sort of irregularly shaped protein, sort of like an extended protein. You might ask why we are including solvent in this kind of calculations. So there are lots of what is known as hydrogen bonds within proteins and between proteins and water that are very important for their function, for their structure. And if you don't have those hydrogen bonds described properly, then the behavior of the system might not be realistic. So that's why, because biology happens in water, we have to have a representation of the solvent in the system. So before we had access to large computers and running large simulations became easy, many people used implicit solvents, like just having dielectric kind of effect present in the system. That actually reduces the number of atoms in your simulation system, but again, explicit hydrogen bonds can be very sensitive to the presence of water. So nowadays that we have really access to large computer clusters, the size of the system is not the major limiting factor anymore. So you can easily go to 100 or 200 processors if you have a larger system. Including explicit solvent in the simulation has become a sort of common practice, which is more accurate. So there is another problem associated with explicit solvent simulations. Anybody wants to guess? So I talked about the effect of hydrogen bonds having a dielectric effect, or having explicit water molecules that can actually replace a hydrogen bond for you, helping you break some hydrogen bonds in the system makes a big difference. But there is another major difference that takes place when you introduce explicit solvent. Anybody wants to guess? There are lots of them, actually. But another one that might make a big difference in terms of what you see in your simulation, how much motion you see in the simulation. Friction. So your protein, if you run it in water, because it has to displace water when it wants to undergo conformational changes, becomes much slower. You run 20 nanoseconds, your protein, with explicit water, nothing happens. You do it with implicit water, suddenly things move much faster because you have less friction. There is nothing to cause friction for you. And if you want to have the right hydrodynamic behavior in some cases, because your system is so huge, there is no way you want to include explicit solvent in your calculation, then you can go back and take advantage of the gamma, the friction damping coefficient that we talked about. So you can increase gamma to a degree that it gives you actually the effect of explicit water in your simulation. So that's something that, again, especially in coarse-grained simulations, so when you go to really coarse representation, it doesn't make sense to have water explicitly in the system. And but you want to have the mechanical properties and effect of water in your simulation, you can take advantage of gamma, increase the gamma to a value that represents the correct sort of water environment. for you. And this is, again, I mean, the block in which you specify, you turn on PME, and you specify the grid sizes. So there is actually a rule here. You are trying to have a product of prime numbers here that gives you the closest value to your X, Y, Z dimensions of the unit cell. Okay. So some of the additional functionalities or things that you can specify in the configuration file that becomes sometimes very, very useful is to constrain and fix atoms. You can turn on fixed atoms and then specify what atoms are fixed by flagging those atoms in this file, in this particular column. We can talk about that a little later. You can fix atoms or you can constrain atoms. Anybody wants to guess the difference? It's almost obvious, but what's the difference between fixing an atom and constraining an atom? Fixing means it doesn't move at all. Constraining means you're adding another harmonic potential on top of the force field that you have. It can still move and fluctuate, but it's not going to be able to move too much away, depending on the strength of the harmonic potential. So these have different functions and different effects on the speed of the calculation and many other properties. So when you fix an atom, it doesn't make sense to calculate the interaction between two fixed atoms, right? Because they are not going to move anyway. So there is no reason to calculate forces acting between two fixed atoms. So if you fix a large part of your simulation system, you can significantly increase the speed of your calculations. Make sense? For example, you have a large protein. I have an ATPase protein, and I'm only interested in the binding site to see what happens if I mutate a couple of residues in the binding site, how many water molecules come in. You can fix the rest of the system and only allow the binding site residues to undergo dynamics. So this way you can significantly increase the speed of your calculations. If you constrain atoms, you are calculating additional terms. Becomes more expensive because on top of your force field now you have these harmonic potentials acting on those constrained atoms. So there is a fundamental difference between fixing and constraining. Usually constraining is better unless you really want to exclude a large part of the system. As I pointed out, initially you want to minimize the system in order to reduce bad contacts, high force regions, high temperature region, however you want to call it, to minimize it, to bring it to a sort of local minimum configuration before you start giving temperature to the system in order to have a stable simulation system. So that was the essentials of the input file. So in the output file, you have the references, et cetera, how many processors you are using. That's actually a pretty good line here to make sure that you are taking advantage of all the cores that are available. You have the energies, as I pointed out. So this whole thing is one line. This is the energy title, time step, bonded energy, angle energy, dihedral, improper, electrostatic energy, van der Waals. All the energy components are listed here. You have the pressure, volume of the system, as well as the temperature. So you can plot these nicely and monitor the behavior of the system. I'm just wondering what the system is because we don't have any bonded energy at this point. So then you see the trajectories are written at certain frequencies. This is the performance information, how fast it is running. You can get an estimate of how long it takes you to run a nanosecond or 2 nanoseconds, or whatever you want to simulate the system for. The example that you will be actually working with is the ubiquitin protein. You can solvate it in a water sphere like this or in a water box. I think you have example files for both systems. if you have problems setting up the system, you can actually make use of the files that are already in the tutorial files. These files are there. You can actually take. The way this tutorial is set up is that you have steps. So you have 1.1, 1.2, 1.3, 1.4, 2.1, 2.2, 2.3. So essentially, you can do either each step on your own and prepare the files for the next step, or you can take the input files from the directory that is in the zip file. I sent you the link to the tutorial PDF file as well as the required files. They come in a zip file or a gzip file. You can download. You will have the whole directory structure. So you can go to that directory and get, for example, a fully prepared ubiquity in a water box, because you are not interested in setting up this simulation. You just want to run the simulation and get the results and analyze it. You can skip some of the steps if you want. So these are the two examples that give you the idea of how to run a NAMD simulation. Then in terms of analysis, these are the equilibrium properties of the system. We want you to be able to look at RMSD of individual residues. You can actually extract the Maxwell-Boltzmann distribution. This is another example, 2.12. You have all the files. You don't even have to run the simulation. Again, if you just want to run the analysis, we have pre-calculated the trajectory for you. You can get the trajectory and do the analysis on those files. But I highly recommend to go through all these steps so you feel more comfortable next time you want to use NAMD on your own. Analyzing energies, temperature distribution, and a specific hits. These are actually some of the examples that are in the tutorial. There is a sort of advanced example on calculating the echo effect, but it's way too advanced. And again, I mean, you can do this on your own later. I don't recommend that for this sort of short 2-day school. So just one note on the on the membrane system, especially since you were asked. So we usually start with the protein structure, and then we try to provide the environment. The environment could include membrane. Usually we have included water as to have the correct environment of the system, and that results in a sort of significant increase in the number of atoms that you have to simulate. But again, that is really the correct environment of the simulation system. So for membrane protein system, in case there is somebody who is interested in membrane protein systems, we have a separate tutorial for preparing proteins in membrane and how to simulate and analyze them. So you can use that tutorial as well. So you will be preparing your molecule, getting the PDB and PSF file, minimize it to relax it, then you heat it to the desired temperature, and you run equilibrium simulations under different ensembles, under different conditions. You can have constant temperature or constant energy. You can have constant volume or constant pressure, again, depending on the ensemble, depending on the conditions that you would like to study your system. Get your data. So far, this is trivial. This is what you learn today and tomorrow, no problem. Or later, you can continue with these tutorials. But then you have to analyze these results and make discoveries. That's the absolutely non-trivial part of this business. But again, that's something I don't think we can teach you here, but hopefully you will manage to do that. So tomorrow we will take a quick look at what is inside these files. I think today would be too much, and we talk about parameterization a little bit. But let me actually jump to. So we will also talk about bias simulations tomorrow, and see what if we want to apply forces and we want to induce certain molecular events. A couple of tricks that you can use. But for today, I would like to actually very briefly in the next 5 or 6 slides just give you one example of application of the method of MD to a biomolecular system. and to demonstrate, hopefully, that this, in general, molecular simulation could be an extremely powerful method if you really take advantage of what is possible in this system. So this guy is an example. The details do not matter here. So this is a protein that acts as a water channel. It sits in the membrane. If you don't have this protein in your kidneys, instead of 1 or 2 liters of urine, you will have 20 liters of urine, which is pretty inconvenient. So some membranes need to be transporting a lot of water. And if you don't have this protein, you will not have this efficiency. So this protein essentially increases water conductivity of certain membranes in humans and in many other organisms, actually. Oh. So this is actually the result of sort of 5 nanosecond NAMD simulations that we did now almost 10 years ago. So this, again, this is what I showed you earlier. So you can see, due to fluctuation, thermal fluctuation of water on both sides of the membrane, you have these transient surges inside the protein, how water molecules move. And what we could describe this behavior for the first time in a membrane channel. We are looking at the full transport without any bias based on the approximate potentials that we described so far, all those crappy force field that we had. Still, we could actually see something interesting. So this was nice, and we watched this simulation, and we thought actually that the behavior of water molecules in this particular water channel was very strange. Because, I mean, again, this was an example in which we watched and we saw something, and then we quantified that. So if you look at the water molecules here, you can see this is already now 10 years old. But if you look, you can see that water always comes in with oxygen sort of heading in first. In the middle, it turns 180 degrees and goes out like this. So really, it comes to the middle like this and goes out like that. So we observed this in a couple of snapshots. Maybe it's random. Maybe it was just those snapshots. So if you analyze this, once you find this feature, you go in and look at the average behavior. This is what you see. Distribution of oxygen and hydrogen molecules over the whole 4 nanosecond production run. And you can see that this confirms oxygen in the middle, hydrogens on the side. After this, you have oxygen, hydrogen, oxygen, hydrogen, oxygen, hydrogen, really confirming that this is a preserved feature in this channel. So we thought we had discovered something very nicely. This is actually something unique. Water doesn't like this bipolar distribution. This is now, if you include also the fluctuation, you can see that in the 2 half channels, it has opposite orientation. This is the dipole moment of water. It fluctuates, but it never flips to the other orientation. So this is unique for water because water likes to have a polarized chain, all the water molecules in the same direction. If you look at it in nanotube systems, that's what you see. It's either like that or like this. So something in the protein is causing this. We thought actually we had a very interesting feature, so we wanted to go publish it in Science. In fact, we did publish it in Science. But instead of stopping here, so we decided to also characterize what in the protein is causing this effect. And that's where the power of simulation comes in. So you can change a lot of things in your simulation system. You can mutate side chains. They do it experimentally. We have to do it too. You can mutate backbone residues. You can assign completely unrealistic charges. So you can have a negative sodium ion in your simulations, right? Just change a number in your parameter file and you have negative sodium ions. You can make a system extremely artificially light, artificially heavy, additional constraints. You can really design simulation systems that address cool hypotheses. And I think that's, again, going back to the discussion about the prediction of the simulation. So you can really take advantage of this tool as an sort of exploratory tool to test different hypotheses. So what we did here is said, okay, so let's see what in the protein is. And that's actually my take-home message, another important take-home message. That so this, you have an advantage here that there are conditions that experimentally cannot be realized. You can do anything. You can play God in your simulation. And if you don't take advantage of this important, powerful aspect, then you are not taking 90% of what's there for you. So you do basic simulation, RMSD, okay, that's it. So let me give you an example. Try to use it. Try to be playful in the beginning. Don't worry too much about having the correct conditions. Let's go to extreme conditions. If something happens there, we can step back and do it more carefully and see if we understand that phenomenon. If nothing happens at 500 degree Kelvin, nothing is going to happen at 100 Kelvin. So take it to extreme conditions, try to be playful, and take advantage of your power over the conditions here. So what we did, so say, okay, so this is the wild type behavior. Now I'm speaking in experimental biological language. The wild type behavior was water was flipping when it goes from one half of the protein to the other. So let's start turning off electrostatic interactions coming from different parts of the protein. And we started doing that, monitoring the behavior of water. The first mutation didn't cause much effect. The second one was significant, but not enough. But when we did them together, when we mutate those effects, then you can see that water sort of recovers its normal configuration. So through this mutagenesis, computational mutagenesis experiment, we proved that, we showed that actually at least within the simulation approximations, within our model, what part of the protein is responsible for this behavior. And this is something that I don't think can be experimentally tested even. So it's not reachable, this kind of modifications that we are doing here. So this really made a big difference in terms of the significance of our finding. It wasn't like just we saw something, we don't know how it is happening, we don't know where it comes from, it's interesting. So we really can show what part of the protein is responsible, what part is this complex molecular system is responsible for these effects. And actually after this work, this generated a lot of additional work. People have been trying to design the same kind of electrostatic patterns in nanotubes, for example, to see the same behavior. And it made a lot of important impact. So that's, please remember that this is a power you have in your hand and take advantage of it. Okay. Good. So I guess so we can have. Let me see actually if we have questions at this point. Yes.
Were they experimenting with observation of the same?
For this, there is no experiment. So they.
Just the observation of the water molecule.
So there is no experiment that can measure this. So this is at this stage. I mean, they can see the position of this protein is. A structure was done in the presence of glycerol at a very high concentration of glycerol. They didn't know where the water molecules inside the protein were in the beginning. After we did this work, our collaborators actually increased the resolution of their structure and removed the glycerol, and they could see the oxygen atoms of water molecules inside the channel, which matches very nicely with our peaks of density taken from the simulation, but they don't see the hydrogens. It's really sort of one of those cases in which experiments cannot measure it, at least not now, maybe in the future.
Actually, one comment is that the simulations can give you insights that experiments may not be able to give some. Probably important to mention.
The simulations can give you insight that
experiments don't have.
Absolutely, absolutely. Yeah, that's again, I mean, sometimes it's completely wrong. We know all the approximations, we know that there are lots of shortcomings. But you know, if I get 5 of these and even 1 out of 5 is correct, we are still doing great. Something that cannot be done even experimentally. And we are getting better and better in terms of understanding where things might fail, binding affinities, things, or where actually things are. In this particular case, I forgot the sort of recipe I gave you just to make sure that this is not the effect of bad charges and things like that. We scale charges down and up for water. This behavior is sort of robust. So this bipolar configuration of water is not an artifact due to bad charges. People did these simulations with different force fields, with GROMACS, using a different set of force field parameters. They saw the same behavior. So it seems that this is one of those phenomena that is robust, insensitive to the choice of force field or approximations in the force field. And so that's one example also of that sort. Good.